All right, welcome back to another little video. Today we're here this morning talking about combinations of functions. In this section, we're looking at how different functions can be combined, whether that be in a piecewise context or through addition or multiplication. So we'll start out with piecewise functions. This is something that you've looked at before. Piecewise functions are functions whose rule is different over different subsets of their domain. These are also called hybrid functions. It's a bit of a mess there. So they're hybrid functions or piecewise functions. They mean the same thing. Function is only continuous when all branches join. So when we're talking about continuity, what we're basically saying is you can draw the entire shape without lifting your pen off the page. And it's important for things to be continuous so that we can perform differentiation and other calculus techniques. A point of discontinuity, it's it means sometimes that there's something wrong with the situation, or it might mean that at a particular point, something in our function switches gears. You're going to see this come up in different contexts. Say, for example, this has nothing to do with this example over here, but let's say that you're driving your car. Okay, so you're driving your car. We have here, this is time, this is distance. I'm just going to create a little graph here. So let's suppose you start driving. So it's the beginning of the time. We start the stopwatch. And you are driving in a straight line at a constant speed. Okay. And now you come to a traffic light. We stop. Notice that the equation has changed what it looks like. So for this first interval here, for the first set of time, so let's say up until time 1, we were driving this amount of distance. So we've so far traveled, say, 30 kilometers. Then we've stopped for some reason. And now we stay at the traffic light for a little bit of time up until time 2, whatever it might be. And now we gradually speed up. So we're going to start out traveling a less amount of distance. And then as the car increases in speed, we travel a greater amount of distance. And then we have here a piecewise graph, and we can see a little application there related to cars. So now let's have a look at this example here, and let's see if we can create a graph related to a piecewise function. So starting out with this one here, we have the function f of x, and f of x has different rules depending on the interval of x values that we're putting in. So for all x values that are less than or equal to -1, the equation is going to be the square root of negative x. For all x values between -1 and 1, we're going to have this equation. And for all x values greater than or equal to 1, we're going to have this equation. So to familiarize ourselves with this, let's consider a few possible inputs. So let's first consider f of -1. Now, f of -1, let's see if we can figure out which one of these 3 rules are we going to use. Well, if we look here, -1 is less than or equal to -1, so we're going to use this rule here because we're in that part of the interval. So let's put in -1 into our equation. We're going to use this equation here. So we have negative of the input, -1. Notice the double negative. There's the one coming from the rule here, and there's the one in the input. So what is the square root of -1? Well, -1 is just 1, and the square root of 1 is just 1. Okay, so that is f of -1. It's just equal to 1 there. Okay, let's now consider f of 0. Now, where in the interval does 0 lie? Well, 0 is between -1 and 1, so we're going to use this rule over here. So what that means is we're just going to take 0, we're going to put it into this equation as our input. So where we see x, we replace it with 0, and now we get 2 minus 0 squared, which is just 0, which means this is equal to 2. Okay, last one, we have 4. So if we put in an input of 4 into this equation, we have the square root of 4. So again, we're looking at this one because 4 is greater than or equal to 1. That's why I'm using this rule here. So we take square root of 4, and then we have the plus 1 at the end there. Of course, square root of 4 is equal to 2. So 2 plus 1 is equal to 3. Okay, so now we've kind of got an idea about how this might work. Let's see if we can now sketch the equation. So in order to sketch this equation, we're going to sketch it using this axis over here. What we need to do is we need to consider the shape of each of the three functions that make up, or each of the three rules that make up the function. So let's first consider this one here. So let's consider square root of negative x. All right, so hopefully we can remember the equation, square root of x. This is something that you're going to have to know. Square root functions, they kind of look like a half parabola starting here and going like that. So they're kind of the top half of the parabola that's been tilted sideways. Okay, now what we have here is just the basic form of the square root function, but what we want to draw is we want to draw y equals the square root of negative x. This is what we call the image, so it's like this basic function that's had a transformation. So let's say this is the old function, this is the new function, or it's the image of the function. Okay, I'm going to denote it using these little lines here. So what's happened is what was the old x is now equal to negative of x. So we can say that the old x is equal to the new x is equal to the old x at the negative of that. And that's how we end up with this value here. So we could write it like this, or we could write it like this. So again, the one with the dash, that's the new one, that's the old one. So what this corresponds to is what's called a reflection in the x-axis. So we had this original function over here. Which one's the x-axis? Well, this is the x-axis down here. So what we need to do is we need to flip that. Sorry, no, this isn't a reflection in the x-axis. This is a reflection in the y-axis. So if we think about this, if we have an input of, say, for example, let's say 1, if I put in negative 1 here, then that's not going to work. So the function isn't going to be defined on this side. The function is only defined for negative x values. So for example, if I put in negative 1, we get out 1. If I put in negative 4, I get out 2. So let me show you how that works. For example, I'll just do it down here. We're looking at the first interval. This is up until negative 1 here, right? So we won't worry about that for now. But I'm trying to draw this. So we have y equals square root of negative x. So let's consider input of negative 1. So what is the square root of negative 1? Well, as we saw before, the square root of negative 1 is just equal to 1. Okay. What about the square root of 0? The square root of 0 is just 0. What else might we square root? Well, we can square root 4. So let's consider 4, it's somewhere over here, or negative 4 rather. So the square root of negative 4 is just the square root of 4, which is the square root of 2. So if we consider that, square root of negative 4, that's going to be equal to 2. So that's there. We have negative 1, which is there, and we have 0, which is there. So maybe the best way of doing this to make it as simple as possible is just consider a few values and see what it looks like. So I'll add the domain restrictions a bit later. I'm just putting down the sketches. In fact, let's add the domain restriction now. So that's what the shape of this part of the function looks like. We are only drawing it for x values that are less than or equal to negative 1. Negative 1's there, so we're actually not going to start here. We're only going to draw from here upwards. So we're going to start there, and we only draw to there. We're not going to draw this part here, because those are not x values that are less than or equal to negative 1. Okay, so let's move on to the next part. We have 2 minus x squared. So again, if we consider the basic function, we have y equals x squared. That is, of course, our basic parabola. That's our basic parabola that we've looked at for a couple of years now. So the parabola, it looks something like that. Now, what has happened to this parabola? Well, you can see there's a negative symbol in front of that parabola. So that corresponds to a reflection in the x-axis. So the graph was pointing up like this, but now if I want to draw, say this is the first image, there's going to be 2 transformations that happen here. This is the new image. So whatever just looking at this negative sign here, whatever this is, say this was 2 squared, we're going to get 2 squared, which is 4, and then we're going to make that negative. So what's negative 4? Well, okay, well, that's just going to be down here somewhere. So we have basically a graph which was a concave up parabola, and now it's a concave down parabola. What happens to that next? Well, if we look here, we have that negative, and then we have the 2 plus 2 over here. So that graph just gets shifted up 2 units. So let's consider, say, for example, on the graph, in fact, I'll just draw it in over here. So we're drawing y equals 2 minus x squared. And let's just consider some values, right? So consider the value 0. So if I put in 0 into this equation here, so I'm looking at what's the y value when x equals 0 for this green graph. 0 squared is just 0, and then 2 minus 0 is just 2. So that's going to be my maximum here. Then let's consider, say, for example, 1. So if I put in 1, we're going to have, so if we have, let's say, f of 1 using this function here, then we're going to have 2 minus 1 squared being 1. So we have 2 minus 1, which is 1. Same for negative 1. So for example, if this was negative 1, what's negative 1 squared? Negative 1 times negative 1, that's just equal to 1. So we get the same answer over here. We get 2 minus 1, which is 1. So parabolas are always symmetrical. They have an axis of symmetry about their center. And if we were to continue this pattern, say, for example, we put in 0. We put in 0 before. So say, for example, we put in 2. Then we're going to have 2 squareds, which is going to be 4, and then we're going to have 2 minus 4, which is negative 2, and that's going to be somewhere down here. So you can imagine the parabola would continue like that, and the shape would be something along these lines. All right, but let's now consider the domain restriction. So over here we can see that we're only interested in x values between negative 1 and 1. So there's negative 1, there's 1. We're only going to draw the function for those particular values of x. Okay, so one last one, and I'll get rid of this stuff over here so that it's easier to interpret. So we've got that middle part of the function there. We have one more equation. We have this one over here. So let's use a different color for that one. Let's say maybe purple. So we're now considering the equation y is equal to the square root of x plus 1. Okay, so square root of x plus 1. This is square root of x, and that plus 1 just means that graph has been shifted up 1 unit. So it's going to be something like that. It's going to curve like that. So it might start here, and it's going to go, okay, let's say we have square root of 1. Square root of 1 is 1. 1 plus 1 is 2. So we have that. And then let's say we have square root of 4. Square root of 4, so 4 is over here. That's our input. So square root of 4 is going to be 2 plus 1, which is 3. So when we get over here, this is going to be there at y equals 3. So therefore, we're going to have a shape that looks like that. You can see it's just the same as what we had here, the orange curve that continued like that, but it's shifted up and it's pointing in the other direction. All right, now again, we consider the domain restriction. So this time we're looking at x values greater than or equal to 1. So I'm actually only going to draw this shape from here upwards. So from 1 and all values greater than or equal to 1. So we're going to continue this shape like so, and then we end up with this pattern. Notice that I have a closed dot here because we're including 1 for this function here, but for this green curve here, we were only looking at x values that are between negative 1 and 1, non-inclusive. So for that green curve there, I'm actually going to use an open dot to indicate that that point is not included. All right, and if we switch over to Desmos, we can see what this function would look like. So here it is. We have exactly what I showed you before. The domain restrictions less than negative 1, we have this equation. Between 1 and negative 1, we have this equation. And greater than 1, we have this. All right, so moving on, let us consider what values is the function discontinuous. So discontinuous means that we can't draw the entire thing without lifting our pen off of the page. Now, going from this orange curve to this green curve, I can draw that in one line without lifting my pen from the page. So it is actually continuous at -1. However, notice that when I get to this part here, I have to lift my pen off of the page. So if I have to lift my pen off the page, it means that the equation is not continuous at that point. So it is discontinuous when x is equal to 1. All right, so therefore the domain, when we're asking about the domain, what we're interested in the x values that could be accepted as an input. So what x values can we accept? Well, like we saw here, the function is pretty well defined for just about everything. In fact, it is actually defined at this point as well. So to check if the domain is always defined, we just kind of look at each of the extreme points. So if we're dealing with a square root function, for example, we consider, could the square root be negative? Over here, we can see that the entire graph is defined for every single value of x. Doesn't matter if the x value is negative, if it's 0, even if it's 1, the answer is going to be 2, because you can see that's why there's a solid dot there. So the domain is in fact all of the real numbers. And the range, can the y value take on every single number? Well, let's think. Y can be 1. If x is equal to -1, we get y is equal to 1. However, y can't be less than 1. So notice that the y values are defined for every value that is larger than 1. Or larger than or equal to 1. For example, we can't get an output of 0. There is no value of x that gives us an output of 0. So we say that the range is all values that are greater than or equal to 1. All right, so let's move on and consider the second half of this exercise. This is about sums, differences, and products of functions. Okay, the basic idea of this is we're trying to combine different functions to create new functions. And these new functions are going to be a little bit funky looking. So as opposed to those basic functions that we started out with, like square root of x, we might have square root of x plus square root of x minus 3. What does that look like? So the way that you're going to be thinking about this is we need to consider essentially the domains of the two functions, the output, so when we combine two functions together, you can see here, it will only be defined for a combination of the two domains of the two functions that make it up. So this is interval notation. What this means is the intersection of the two domains. So what I've written here is if we have f and g, they're two different functions, these functions can only be defined when both functions are defined. So what I mean is a combination of these functions, I guess it should say. So let's say combinations of these functions can only be defined when both are defined. So for example, if d of f is the domain of f and d of g is the domain of g, the functions are combined with a domain of the intersection between those two domains. So in other words, where the two domains overlap. This is given the notation f plus or minus g, which can be written like this, or if we're multiplying them, it can be written like this. So best way to do this is through a couple of examples. So let's consider these two functions here. What do these functions look like? First up, so we have the square root function. In fact, we can just draw it over here. Let's say we have the square root function, basic one, looks like that somewhat. This square root function, square root of x, has been shifted back 4. So remember, if there's a plus underneath here, that means shifting to the left. So it's been shifted back 4. It's now starting here. So for example, if we put in, let's say 4 plus 0, what's the square root of 4 plus 0? So the square root of 4, that's 2. So when x equals 0, we get out an output of 2. So I'm just going to be drawing here f of x. That's in blue. What about if we have, let's say, what's a good number? Let's say this is 5. If this is 5, then we're going to have square root of 4 plus 5, which is the square root of 9, which is 3. So over here at 5, we're going to be getting 3. And you can see that there is the shape of this square root function, something like that. Okay, what about this other one here? I'll draw this one in reds. let's suppose we consider a couple of values. You can see there's a negative sign in front of the x. That means a reflection in the y-axis, so it's been flipped like that. And just consider a few inputs to see what this equation might look like. So for example, if x is equal to 4, if x is equal to 0, then we're going to have 4 minus 0. So square root of 4 minus 0, that's just equal to square root of 4, which is just 2. So we still have this output here. And if we consider, say, for example, 4 minus 4, what's the square root of 4 minus 4? That is equal to the square root of 0. So when x equals 4, y equals 0. So we're here on the y-axis. And finally, let's say we consider our old friend -5. We have 4 minus -5. 4 minus -5, that means 4 plus 5. So now we're looking up here at an output of 3, because the square root of 9 is equal to 3. Okay, so now we have here the basic shape of our curve. There it is. Okay, so now I've just drawn f of x and g of x. So in order to draw this, I want to draw f plus x. I'm going to do this one in green, and this is what the question's actually asking. So in order to draw f plus x, what we need to do is we're going to use a method called the addition of ordinates method. And essentially the idea here is we're going to look at different extremes. So for example, we might look where the two functions are the same as each other. Notice that the two functions are equal to each other at this point here. So what is 2 plus 2? 2 plus 2 is equal to 4. There it is. So all I'm doing is I'm just considering particular values, having a look to see what the function looks like at that point. Okay, how about this one here? So this is where one of the functions is equal to 0. So we have here, forgotten which one's which, so let's label them. The blue one is f, and the red one is g. So let's consider this one here. We have g is equal to, sorry, that was g in red. Very important to get that right. So we have g is equal to 0, f is equal to something over here. So whatever this value is, if we have f plus g, so something plus 0 is just equal to whatever this was, because we're just adding the two values. Same over here. So if we add this red point here, so I'm looking at this point here. If I add this red point here to this blue point here, the blue point's just equal to 0. So anything plus 0 is just equal to whatever we started with. So we have that value there. And then we can kind of see what this shape is going to look like. It's going to be something like this. And what about, we might ask, the values outside of this range? Well, like we mentioned before, the combination of these two functions is only defined when both of the two functions are defined. So as we can see, the blue function is not defined for values less than -1, because then we're going to end up with the square root of a negative. And the red function is only defined for values less than or equal to 4, because then if we're outside of that range, then we're going to have the square root of a negative number. Okay, so therefore we can see that this green curve here, that defines the entire combination of this function. All right, let's do one more example. So actually, let's just finish this up. So the rule for f plus g is going to be just f, what are we trying to do here? The rule for f plus g, I think, is what it's wanting. So the rule for f plus g of x is equal to what was f, which was 4 plus x plus square root of 4 minus x, okay? So that's the overall rule when we combine these two things. And of course, the domain is equal to, well, it's defined for all the x values that are between -4 and +4, including those two values, because at those two endpoints, this function was equal to 0, this one was equal to 0. So they're well defined at those points, so we can accept them. All right, so moving on, we have f times g. So f times g, what we're going to be looking at is the square root of 4 plus x times the square root of 4. Let's do this in a different color. So the square root of 4 plus x times the square root of 4 minus x. Okay, so what we're doing is we're combining these two things. Now, unfortunately for multiplication and division, it's not quite as easy as addition in the sense that with addition, we can just kind of do the addition of ordinates thing. With multiplication, it's best to just simplify the function and see what it comes out as. So let's have a look at this. Let's see if we can remember our surd laws. So if we have, for example, the square root of something times the square root of something else, that is equal to the square root of that first something times the square root of the second something. So applying that logic over here, we have the square root of 4 plus x times the square root of 4 minus x. That's all underneath one big square root sign. And then we just have under here a difference of two squares. So when we expand that, we have 4 times 4, which is 16, minus x squared. Okay, so that's what we get when we multiply these two things by each other. Okay, so therefore we can see that we have square root of 16 minus x squared. And if we recall, this is actually just the top half of a circle. So if we were to try and rearrange this, we can see that this is the square root of 4 squared minus x squared. So this here would be a circle. If we were to rearrange this, for example, we might remember that if we have the equation x squared plus y squared is equal to some number squared, that there will be a circle with a radius of r. So if we take f of x to be our y value, we could rearrange this, we could square both sides, we get y squared is equal to 4 squared minus x squared, and then we can minus x squared from both sides, so we get y squared plus x squared is equal to 4 squared. So we can see this takes on the basic shape of a circle. And we're only going to be accepting the top half of this circle because we have a square root sign and the square root thing underneath there has to be positive. So essentially, this is going to be a circle with a radius of 2. So it's just going to be something like this. It's going to start there. It's going to go down to there, it's going to go down to there, and we're going to draw a circle shape. It's going to be something like this, and that is going to be the combination of these two functions. So basic idea here, if we're adding or subtracting the two functions, try this addition of ordinates method, and if we are multiplying the two functions by each other, just before the multiplication, do some algebra and see if you can look at the rule and figure out, based on what you know about those basic functions, including circles, might need to look back over those, what the graph might look like. Here that is on Desmos. So we have here when we added the two functions, we can see there's the combination of the two that we had before. And then if we multiply the two functions, we get this purple graph. It's the top half of a circle. All right, so we move on down to the next part here. So this is what we were talking about, addition, subtraction of ordinates. Consider the endpoints, the extremities, etc. If we're squaring ordinates, we can remember our squaring facts, like 0 squared is equal to 0, negative 1 squared is equal to 1, etc. All right, so continuing down, let's do a few more quick examples and then we can move on. So looking at some graphs, we're going to apply this addition of ordinates method. This technique, again, we just look at the extremities. So first up, I'm going to consider this point here. What I want to draw is f plus g. Okay, so let's look at the f function, the g function. They're both equal to the same thing at this point. So whatever that is plus whatever that is just going to be 2 times that point, isn't it? Same thing over here. This might be a good one to look at. Well, actually, let's consider this point here in the middle. So what we have here is a hyperbola, the purple one. What did we say before? Well, we said that in order for the combination of the functions to be defined, both functions need to be defined. Now, f is actually not going to be defined when x is equal to 0, is it? That's an asymptote there. So we know that this green function, the combination, will not be defined when x is equal to 0. So it's going to be defined for all real numbers except 0. That's what I'm trying to say here. Okay, next up, let's consider the extremities. So that's what it says here. We've considered the endpoints, the key coordinates, the extremities is next. So first up, let's consider what happens as x goes towards infinity. So as x goes towards infinity, f of x gets really, really small. G of x gets really big. What is a large number plus 0? Well, it's basically going to be just that large number, right? So whatever this number here is, plus whatever this number here is. So what we're going to do is we're going to be, as we get closer to 0 over here, this curve, the curve of f plus x, is just going to get really close to g. So we're actually going to have sort of like an asymptote occurring along this curve itself. Same thing happens over here. If we have, this is 0 down here. So g of x is equal to, so g of 0 is equal to 0, we can see. So what's 0 plus a number that is effectively infinity? Because as we can see, as f goes towards, sorry, as x input goes towards 0, the output of f of x goes towards infinity. It shoots up like this. So what we're going to have is we're going to have a similar behavior on this side. So these are our two extremities. So as g goes towards 0, we're going to have f plus 0, which is essentially going to be just f. It's never going to quite reach that because f is never going to be equal to 0. Sorry, x is never going to be 0 in this equation here, but we're going to have that sort of shape. Same thing on this side. If we consider, say, for example, let's choose the same ones again. So let's say we have what is effectively infinity for g. So this is going up towards infinity. This is going towards 0, but it's approaching it from the underside. So it's going to be a number that is slightly less than 0. So what's a really big number plus a number that is slightly less than 0? So that basically means like what's infinity minus 1? Well, it's going to be a little bit less than infinity. So we're going to have asymptotic behavior that is approaching this line here. It's never quite reaching it, and it's approaching it from the underside. Let's consider another point. So say, for example, look over here. There's going to be some point where these two functions are equal distance from this x-axis here. At that point, if we have, say 1 plus -1, that's just going to be equal to 0, isn't it? So at some point, these two equations are just going to add together to make 0. So that's going to be another key point. And then if we consider over here, as this number here tends towards negative infinity, we have a number that is slightly larger than 0. And we have here basically a really small number, so a really big negative number plus a really small positive number. So that's basically like a negative number plus tiny positive number. It's going to be slightly larger than infinity. So we're going to have this kind of shape going like this. So that is kind of the curve that we're looking at there, the green curve. Let's do another quick couple of examples. So going through this again, so this is b, we would just consider when the two values are equal to each other. So here the two values are equal, they add together to make, so again, we're looking at f plus g. They add together to make a number that is double their size. As this one here gets really large, we kind of have the same shape as before. It's just been shifted down a little bit. So as this one here gets really large, we have a really large number plus, I guess, 1. So as this tends up here, we're going to have big number plus 1. It's going to be slightly larger than that first big number. As we tend in the other direction, we're going to have really small number, so effectively 0 plus a number that is larger than 0. So we're going to have a shape that looks like that. Okay, and then over here, there's going to be that weird point where the two graphs are equal distance from the x-axis. It might be somewhere around there. At that point, f plus g, they're going to cancel out with each other. We're going to have a value of 0 as our output for f plus g. And then if we consider the other extremities, so we have a really small negative number plus another negative number that's just a little bit small, like this. It's going to be basically a number that is tending towards negative infinity again. And on the other side of that, we're going to be tending towards positive infinity, where we have, and again, it's sort of approaching this curve here. So we have basically a really big number plus really small number. It's going to have this cubic sort of shape there. All right, and I'll leave this one here as an exercise for you. One last question here. This is a I might need to scroll down here slightly so you can actually see this. Hopefully you could see everything before. Actually, let's just do it like this. So I will add a new page and the end here, just so I can actually scroll down so you can see this. Oh, that's not working so well. That is all good. There we go. Okay, so now you can actually see that. Okay, so we have the graphs of these functions here. This is an exam style question. So how would we answer a question like this? We want to figure out what's the relationship between these three graphs? So we've combined two graphs in some way to make a third graph. First thing that you need to notice about a question like this is that G and F are facing one way and H is facing the other way. So what that's telling us is that H is a difference of the two other equations. So H might be F minus G, or H might be G minus F. So essentially, we can go straight to one of these two possible options, D or E, as our answer, because they're facing in other directions. Now let's consider which one might be true. So let's say, for example, we consider this realm over here. So we can see that H is less than 0. So is it F minus G? Well, that would be a larger number minus a smaller number. Large number minus small number, that's a positive number, but we get an output of a negative number. So let's consider G minus F. So G minus F, that would be a small number minus a number that's bigger than it. So say, for example, we have 1 minus 3. That's equal to a negative number. Yeah. So therefore, we can see here we have an output that is negative. So that clues us into the fact that H of X is probably going to be E. It's probably going to be D. It's probably going to be this one here, G minus F. But we can give it another couple of examples. So let's consider this in-between region over here. So we have, for example, G, so this number here, minus this number here, or maybe let's consider one that's even more obvious. Let's consider this point over here. So we have the pink curve, so G minus F, which is the blue curve. That is a positive number minus a small number that is a little bit less than 0. That comes out to be a positive number there. So it does make sense that it would be the curve down here. So essentially the basic idea for this, and the answer there is, of course, H is equal to G minus F of X, so the answer is E. So yeah, some basic strategies for addition of ordinates. Just consider a few different values of X. It might be helpful to draw like a little dotted line, see how the points are being added, and then of course consider the endpoints and extremities first, and the key coordinates such as intercepts, or the values at which both the functions are equivalent to one another. All right, that's all for today's video. I will see you guys soon. Thanks for watching.